So without further delay, here's your Delphi instructor.
Hello, Dave Hobbs for Delphi here. Thank you for logging in to our live cast on Keeping the Spark Alive, Coil-On-Plug Diagnostics. Let's get started about what we're going to be going through in the next hour. Jam-packed information for every level of diagnostics wherever you are in your role of doing drivability. We're going to talk about the fork in the road briefly, air and fuel, determining if I have a coil-on-plug issue or some other issue. We'll do a little quick review of Ignition 101 so we can bring what we know from ignition coils to the present day 2, 3, and 4 wire coil-on-plug systems. We'll go into the bench testing of what we can and cannot do depending on the type of coil-on-plug design, and we'll also work on vehicles, 2 vehicles live here today, working on using a scope, using a multimeter, using an amp clamp, and just using good old common diagnostic common sense. So that's what we're going to do. And then finally, we'll summarize it up with some questions to you folks. You can write questions back, and not to mention some last minute common sense things on things that can rob spark from the vehicle. Let's get started with a little review of that fork in the road. When you have an ignition misfire suspicion, always good, no matter what you think's wrong with that car, to run all DTC check in every module. Remember, it's not just a powertrain or engine management system. It's a complete vehicle where a lot of things are overlapping and working together in concert. So run all modules, all DTCs, and especially in the PCM, look for those pending codes to get the big picture. Remember, you could have an ignition module that's not the problem. Ignition coil can make spark, but it could be some diagnostic circuit that makes the computer think it's not working correctly and shut the injector down. You have a misfire. It's not really a misfire. So more on that later. Also, other information to help supplement your DTCs, your failure records, pending codes, and so forth would be Mode 6. We did a complete broadcast in recent months on Mode 6 with hands-on case studies. So make sure you go to the Delphi Auto Parts YouTube page and look at the Mode 6 program we did in the past. If you're not a Mode 6 guru, you're not comfortable with it, you'll find it has a lot of extra help, especially with Ford misfires, because that's one of the Mode 6 parameters that is there on Fords. It'll help you a bunch with that TID 53 or SID 80 on the newer CAN bus vehicles, knowing which component failed, at what level it failed, and so forth. So bone up on the Mode 6. That'll help you a bunch, deliberately knowing how bad the cylinder is misfiring and which cylinder it is misfiring. Now, every cylinder, in order to not misfire, has to have good power to the coil. So voltage drop testing, make sure you're comfortable with that, you're doing it correctly, whether it be a simple 2-wire Ford or Dodge coil-on-plug, where we have power from the ignition fuse and a ground supplied by a coil driver, a high current coil driver in the PCM. Where we don't really have a module here, this is just a coil. This might as well be a 62 Chevy oil-filled tower-shaped coil from the past. Its functionality, that's what it does. Secondary output, primary windings, power from the ignition fuse, a ground supplied by the computer. Or a 4-wire coil with a diagnostic circuit, a feedback circuit. They all pretty much work the same, as we'll get into. Now, we'll go ahead and talk about coil as a coil, whether we have a single coil for the entire engine distributed like we see here on the far top right, or this 4200 coil-on-plug from GM, this little Delphi coil that's a 3-wire, a 2-wire pencil coil, even a DIS coil. They work the same. Step-up transformer. Let's give a real quick treatment of the theory of what a step-up transformer or ignition coil does, so you can understand some of the things we're going to see on the car with a meter and a scope, and so you can understand a little bit what we can see on the bench as well with an ohmmeter. First off, we have battery supply, and we're going to have a coil winding, one of 2 that's inside of every ignition coil there ever was. There's a primary winding and a secondary winding. Little review here, I know, we'll get through it quickly. The primary winding is the shorter one. It'll have a few hundred feet as opposed to the secondary winding right next to it, several thousand feet of winding. Therefore, its resistance is lower, somewhere between 3 or 4 ohms down to 0.5 or 0.6, a little less than half of an ohm we can see in some applications. Here we have 3 ohms. When that switch closes, that switch used to be the points in an old-fashioned conventional distributor. Today, it may be a transistor inside this smart 4-wire Toyota Coil-On-Plug. but that transistor is going to be the equivalent of that switch you see here. When it turns on, we're going to slowly, now slowly as far as in milliseconds, take a magnetic field and build it up. Think of this coil, primary winding, as like a bucket filling up with water. It takes a little while to get it full. We're going to see that next in an illustration talking about using an amp clamp and a scope to measure the current ramping of a coil. So as that field builds up, it makes this an electromagnet. Some techs actually have a process where they use a little ferrous sensor type device, hold it up to a coil, and while the engine's running, if they feel a little bit of a magnetic pull, that coil's working. That's good old-fashioned see-the-pants MacGyver type testing. That's fine. When we see the picture next here, as that builds up, that's critical to see. If you use an amp clamp and any kind of a scope, let's say it's built into your Modus, your Varus, whatever you have, maybe you've got a 4-channel Pico scope like I've got, it all works the same. It will build up slowly. That ramp up is normal. If we don't see a ramp up, if we just see that coil turn on, or the transistor turn the coil on like this and turn off abruptly, that turn on abruptly means it's not really a coil. It's probably a short circuit, maybe something else besides the coil there across there. There's been cases where I've seen water intrusion into coil connectors, into the electrical connector right here, causing a little bit of a short from the B+ across another terminal, and that can knock out the modules eventually, and that can cause issues where we don't see the right current ramping of the coil. So make sure you see that happening. When the switch opens, when the transistor either in here or in the simple 2-wire coils under the hood in the computer, the PCM, when that turns off, that's when this big old magnetic field now collapses suddenly. That creates something called self-inductance, which if we could back probe, in the 2-wire coils, we can, we'll find that out in this broadcast. The back probing of the 2 wires, one of the 2 wires here, we'll see a spike on a scope that can be 50, 100, 200 volts. That's called self-inductance. That's not enough to fire that gap of air in that spark plug, but it's enough to make a sudden change of the coil next to the primary winding, which we don't see in this picture, but we do see here the secondary winding, which has 1,000 times more, 100 times more turns ratio. So we'll see several thousand ohms of resistance in the secondary winding. When it is exposed to a self-inductive kick on the primary, we have what's called mutual inductance, and that's where we see 200 or 300 volts become 20 to 30,000 volts. Step-up transformer theory 101. So most of you remember that, I hope, but just in case we need to brush up so we can move some of this theory into practical reality coming up right now. So as we see the ramping up using an amp clamp and a scope, and we basically taking lots of pictures, if you will, like we would if we had a meter, just watching it step by step. That's all a scope does. We're going to watch that progressively build up. When the coil is turned on, the primary winding's turned on, and we turn it off, we see a quick shut off. That's normal. And that's when we see the high voltage and self-inductive and now mutual inductive kick, even higher voltage, occur to make enough juice to ionize that air gap and make the air-fuel mixture burn under all conditions. That's all what's going on. It's been the same since that 62 Chevy Tower oil-filled coil that I worked on when I was a kid, and if you're old enough, remember that as well. And it's the same way on these modern day coils. So coils are coils. Let's get into the 2-wire coils first before we get into the more advanced coils that have 3 and 4 wires in their small connections, electrical connections. So let's take a look at applications. A lot of Chrysler, Dodge, Jeep. We're looking at some of the Fords over the years. In fact, until most recent years, they've all been 2-wire. Just noticed this year, 2016 model year, we've seen some 3-wire smart ignition Coil-On-Plug Ford applications. But there's a remote driver. That means the high energy, or I should say the high current turn on of this 0.6 ohm load in this Ford coil is coming from the PCM, the coil driver module or ignition module, as we used to call it, mounted in the PCM, and an output for each of the 4, 6, 8, whatever in coils, Coil-On-Plugs. So pretty much straightforward. Bench testing we're going to look at next is the same as if you were measuring one of these or one of these. They are pretty much the same. You can check primary and secondary winding resistances with an ohmmeter on the bench. So before we go to the bench, take a real quick look at electrical theory, how it's connected together. At the very top of that schematic where you see the primary and the secondary winding, we see a connection And we'll see that with the ohmmeter. We see where that secondary winding terminates at one end on the spark plug, on the other end, typically at the primary, with the source of the primary. Now, that can all be checked. 1.5 ohms, it might be 0.5, 0.6, doesn't matter. We're looking for an open circuit or hundreds of ohms. That would be abnormal, and that would be a coil that would not fire, and there'd be no spark at all, and definitely DTCs and so forth for that cylinder. Measuring between the secondary output and one of those primary terminals, which we'll do on the bench next, that's going to be several thousand ohms. We're measuring the secondary resistance of the winding. And then thirdly, we're going to make sure we don't have any shorts between either primary terminals and chassis ground. That should not be there, so that's the case. Now, a little course of buyer beware, if you will, tester beware. I'll talk about this in the hands-on bench portion. There are sometimes a replacement of that little jumper between the primary and the secondary with a diode, sometimes like a Zener diode. It takes, let's say, 70 volts to jump across. Therefore, you may see resistance several thousand ohms when you move your meter one way, reverse the lead, you see OL, or you just don't see anything. So don't be discouraged. I'm going to tell you which coils you can and cannot test reliably on the bench with an ohmmeter coming up in this next session. Hands-on, what's going on the bench. Ignition testing on a workbench has been a tradition since the early days of ignition. If you're old enough tech to remember the old oil-filled tower-shaped coils, it's very simple. You want to measure the primary winding resistance to make sure you didn't have an open, because it's not going to work if there's an open circuit. Had to be a complete circuit, an ohm or two typically were some numbers you'd see. The secondary winding would be between one of those primary winding towers where the small wire would go to from the points, or more newer cars, the ignition module, and the secondary output. So that was the connection for one side of the secondary. We can do the same thing with a little bit more modern ignition coil and then bring it forward to DIS, and then finally today's topic, Coil-On-Plug, so you can see the transition of what you can and what you can't do. Here is an old coil from like this GM system, would be the distributed systems, single coil. We're going to go between the two primary windings, the power and the ground that's supplied by the ignition module, right here, my finger's tapping. And we should see maybe, I don't know, 6/10 or so of an ohm, exactly what we're seeing. We're seeing about 0.6 due to Ohm's law. That's going to be 12 divided by 0.6, about 20 amps peak when this thing is fully saturated. So we're making sure that primary winding is not open. If it's open, there's no spark for any cylinder in this case. Now we can also leave one of these terminals there. They're only going to be 6/10 of a difference, of an ohm difference, and move over to the secondary output of the coil. Get a good connection here, and that's going to be testing the continuity of the secondary winding. A lot more turns of coil, a lot more resistance, and we've got about 8 with a K, 8,000 ohms. We could actually have an open secondary condition in the coil. It would still fire. It would just jump another gap. You might think of any gap inside the coil as like a spark plug gap. That would just be a problem with the coil, but it might run. It could be an intermittent problem. Now these tests, we can fast forward to DIS. Same thing. They were pretty cut and dry. We're going to see it's not so cut and dry with Coil-On-Plug here in about 60 seconds. So now we can do the same testing here. Get my probes, go into the primary, and the DIS was really cut and dry. You can measure the primary like we're doing here, and we've got 0.6 once again, so about 20 amps is going to flow when that primary is turned on by the ignition module. And we can also measure the secondary winding resistance to see if we have an open. Remember, it may still fire, but it would probably break down under a load because we have one more spark gap actually in the coil. And that can sometimes cause carbon tracking, both internally and what you can't see. You can only see under a load when it starts breaking down, or externally. You may be able to see some telltale signs of that. And we are seeing about 5,000 ohms. So that's the secondary winding resistance. So this coil, at least on the surface, electrically, primary and secondary have good continuity. It's good. So we have a couple old-fashioned coils that we've tested, and you're probably familiar with that and have been for years. Now let's apply that knowledge going forward to a Coil-On-Plug Ford style 2-wire So we still got the output of the secondary. I guess you could call that the third connection where the spark plug is going to go. But up top, where the harness plugs in for each individual coil, we're going to have two wires. One's going to be the ignition feed. The other one's going to be providing a ground whenever that coil needs to turn on, saturate that primary winding, and then turn off, of course. That's when the spark occurs in the secondary, the self-inductions turning into the mutual induction. And that's what we can measure the primary right now, which we are with a couple jumper leads, and we're seeing about 0.8, so that's a little less than 20 amps, so still considerable amount of current draw. That's going to really build up a field. We turn that off, and that's going to make the secondary. Now, what can we do to measure the secondary winding continuity? Same thing we did with these older coils. We can go leave either one of these plugged in, unplug the other, pocket screwdriver, go into where the spark plug is going to go against the spring contact that goes into the output of the Coil-On-Plug, the C.O.P., and we've got about 6,000 ohms, 6K, 6,000 ohms of resistance of the internal winding of the secondary winding. If that was open, you could dim the coil. It might still run, as we've said. If the primary is open, you definitely can dim the coil. You always dim the coil either way if you have an open circuit, but you know it's not even going to fire that plug at all. So those are some bench testing we can do. Now we'll see how convoluted it's going to get next when we go into some of the 3 and the 4 wire coils. Here we have a 3 wire coil. Probes here. And as I measure, let's see here, one terminal to the next, I see some high ohmage, a kilo ohm, 8 kilo ohms. We're just measuring electronics is all we're doing here. This is a power, ground, and signal wire type of connection. So there's a small module in here, and you're not really measuring a winding at this point. Now, where does the secondary get back into here like it did in these coils? That's going to be a little hard to determine too. A lot of these modular type coils, more than 2 wires, 3 and 4, there's blocking diodes to prevent you from even trying to do what we're trying to do right here. So what I'm saying is, if you don't have 2 wires, like the Ford Coil-On-Plug, you're not going to have much luck doing any resistance bench testing on either the primary or the secondary winding. That's an OL, that's an OL, that's an OL, open, open. Looking at the whole diode aspect, I'm just going to reverse the polarity here. Go like this. Now with a reverse polarity, do we see any difference? We may or may not. We did, 7,000 ohms, 7 mega ohms. So those are some of the diodes the engineers were telling me about earlier when I called them today to find out, hey, what can I do and what can't I do on a 3 and 4 wire coil? And basically, I'm just seeing the presence of a blocking diode and the electronics internally, what's going on there. I'm not measuring anything when it comes to the continuity of the secondary or the continuity of the primary. That's why we have to do the on-car testing, looking at the pattern of the trigger, triggering this thing, looking at the current draw of the coil, because the coil is not building up a field and then turning that off, and we don't see that ramp up with an amp clamp and then back down, then it's not working. And so that's the modern way of checking the coil out as opposed to just using the ohmmeter like we used to do. Wrapping some of this bench work up with what we see here on our screen, 3 wire, I'll call it smart, early GM smart Coil-On-Plugs. If you recognize that particular shape of the coil, that's that Delphi 3 wire 4200 inline 6, that Vortec engine. This heat sink is common electrically, 0.1 ohms, with the mounting bolt. But the ground is a little different resistance level than this ground right here. So basically, like I said in the hands-on portion, you want to make sure that you either absolutely know what you can do on the bench, otherwise more than 2 wires, you're not going to do bench testing. As you see on this PCM, you see the EST 1, 2, 3, 4, 5, and 6. I want you to think of those circuits as very low current signal lines, kind of like a mass airflow sensor or a serial data bus line. They are not actually doing any current control. They're just triggering the transistor in here to do the current control of this particular coil. So for that reason, we'll see a square wave. We won't see any kind of an inductive kick. We won't see an ignition pattern like you would see on a 2-wire coil or an old-fashioned car's ignition system either. So those are 3-wire coils. They come in places like Nissan and Honda, BMW, the early GM I mentioned. So again, no bench testing, just go right to the car, do the testing we're going to do here coming up on both a 2-wire Ford and on this Camry behind me. We'll do a 4-wire smart coil bench test or car testing there as well. Now looking at more of the schematic of how these things are laid out, here is a typical test we used to do in the pictures of those old tower-shaped oil-filled coils on the left. Looking at primary resistance, we were trying to do that in the bench, and on the 2-wire Fords, we could do that. And we saw 0.6 ohms. We could not do that on the 3 and the 4-wire coils. And looking between secondary and either primary lead, as we see a traditional looking coil, if you're old school like myself, you'll kind of relate to that. You see several thousand ohms, things you can't do with the Coil-On-Plug 3 and 4-wire circuits, because what you see in the schematic on the right, where I'm starting to now have the power lead going to that bottom side of that primary winding and goes over and captures a spot where the ignition feed is to the coil terminal itself, the connector, and then the ground provided by that NPN transistor, the coil driver, built into this guy right here. You can't get to those with your meter, therefore you can't measure that primary winding or, in many cases, the secondary winding either, because that's all secured internal with electronics and sometimes blocking diodes. So the old GM 3-wire C.O.P.s, sometimes a mounting bolt made the ground that was there for you, and other times you could measure resistance between at least secondary and one of those terminals. Sometimes you couldn't. So it all varied. So again, I'll make the point really clear. You got more than 2 wires on a Coil-On-Plug, you're doing your testing exclusively on the car and no longer any resistance testing you can rely on. Now, let's talk about some things that could cause us to think about what makes Coil-On-Plugs modules go bad. What makes C.O.P.s go bad? Well, the same thing that makes any coil go bad, whether it be an old 62 Chevy Tower oil-filled coil or a brand new 2016 Chevy with a 3-wire smart coil go bad. Open secondary, that can cause coil damage, it can cause module damage. So think about it, if you got more than 2 wires, you got 2 functions here. You have basically an ignition coil and an ignition module. That's what's in all of these that have more than 2 wires to the connectors right here in the harness. They are ignition modules and coils built into one. And so what can kill an ignition module? Well, high voltage spikes, EMI, bad grounds, intermittent power sources. Spiking can cause module failure. They don't like that. They don't like excessive heat, and they don't like excessive vibrations. They don't like to be dropped either. So if that happens, you might not want to trust that coil. You might want to get another new one out of the box because it may fail either immediately or soon after you put it in the car. So it's like any other module. You wouldn't drop a PCM, 3 or 4 feet to the ground, pick it up and throw it in the car. Same thing here. So if we have an open secondary or super high resistance secondary, and many of you remember cranking the engine on an old HEI car with a distributor, and maybe it was somebody else's car, maybe you're just moving it from one stall to the other, or maybe a service advisor did that to you, and you went to lunch to go get some spark plugs on your way back to the shop, and now all these spark plugs are out of the engine, the plug wire is just hanging there, somebody cranks the engine over, you remembered what happened, right? If you're old enough to be a tech in those days, the ignition module got spiked as all that high voltage was built up in that old coil built on the top of that distributor, and it just killed that module. So the spark occurs that can kill modules. The same things that happened with the HEI coil in distributor can happen with Coil-On-Plug when we have an issue with high voltage secondary having a problem, either because of a bad plug, it's essentially open, it's so worn out it might as well be open, or something has happened to the spring, some overheating issue, corrosion, rust, whatever got in here, or somebody left it out, it's the wrong one, you don't have the right application, therefore this is not fitting firmly down in that head on top of that spark plug. corrosion on the plug terminal itself, any of those things that cause excessive resistance, cause that voltage that's being built up to look for another path to go, it could knock out the transistor in the module section of the COP. So there's an issue. We can also have internal crossover called carbon tracking. Make a little trace like a scar internally between the primary and the secondary, zap like that, and that's when we have a permanent trace that even when the secondary high resistance issue is repaired, example being this GM coil near plug, where I have a short little plug wire going down to the spark plug, if that's got high resistance because of the internal circuitry of the plug itself, or because of maybe the connection at the plug wire terminal onto the spark plug, whatever the case may be, any high resistance secondary, higher than normal, can cause the spark to say, you know what, why don't we just jump across from the secondary to the primary? That's a good path back to where I started, and it makes that trace. Now you fix that plug wire or that worn out spark plug, and now it runs okay at idle and light throttle, but when you have tons of air packed into that cylinder's air gap in that spark plug under heavy load, that's when the voltage demand is so great, the electrons taking the path of least resistance say, you know what, why don't we go jump across that little scar tissue, that little carbon trace that was burnt internally between primary and secondary windings. Now sometimes external carbon tracking can be seen visually. You see little burnt little arc marks. But if you don't see that, it could still be inside, and it would only miss out sometimes, in some cases, under load at the worst possible scenarios. You have a very intermittent ignition misfire. So the same things that's been happening with DIS, even the older systems, occurring with the coil-on-plugs, and because they're a little smaller, a little lighter weight, they tend to be a little bit more prone to this. That's why you're putting more on than you used to with a single coil mounted somewhere in a lesser hot spot of an area. Now let's go to the car and look at what we can do with a meter, an amp clamp, and a scope. So whatever you do, whatever your tools of choice are, on a Ford 2-wire coil. Okay, time for some hands-on on the vehicle with Coil-On-Plug 09 Ford Flex. Which cylinder is actually misfiring? That's why we had a broadcast last year that you can look up on the Delphi YouTube site and find all about Mode 6, because Mode 6 was really kind of made for us to determine which cylinder is misfiring. Now what we're going to do here is we're going to look at simple power to the 2-wire coil-on-plug on key up. We're going to look at it two different ways, once with a meter, once with the scope. And of course, I'm using the back probe of the two connections. Now, since we have a primary winding, which we actually are hooked into right here, power from the ignition fuse goes to one side of the winding, and a ground, when the PCM applies it, goes to the other side of the winding when we want the primary winding to saturate, build up a magnetic field, so we can then collapse it and create the self-inductance, which causes the mutual inductance of the much longer, larger secondary winding to make the spark. So what will we see between chassis ground with the meter? I got my black lead on ground and the red wire going to the ignition coil. Let's go ahead and see. Turn the key on. Watch the meter, 13 volts. Now, if you want to see if the coil has continuity, it's not an open circuit. Let's say you had a P0301 on the cylinder and you're not sure what it is. Really quick, something you could do before going in further, the air, fire, fuel, which is it? Just check the coil out real quick. It's easy to get to in this model. I'll take the plenum off like some of those back cylinders, and we'll move our lead from my back probing from the positive feed to the negative feed, the side that gets the ground from the PCM. Guess what we got here? 13 volts. What are we measuring? We're measuring open circuit voltage. Since there's no ground applied by the PCM to the negative side of the ignition coil primary winding, we're just simply seeing all that power going through the winding, waiting for that ground. So we're seeing the source, not the source side, we measured that originally. Now we're seeing the side that gets the ground before the ground's applied. Now when we start the engine, go ahead and start it up, Allison. The voltage is slightly lower in the meter because we're seeing an average on versus off time. It's mostly off and a little bit on. That's what the voltage down just a tad. Now if we change it to something more realistic with the meter, because the meter's now seeing the negative supplied ground from the PCM, we should see a pulsing circuit. We'll turn it to frequency, and sure enough, we see a steady 25, 26 hertz. That's 25 to 30 times per second that cylinder is hitting, that coil is working. So that gives us two or three things. We're getting a pulse from the ignition coil. We've got a good primary winding for both power and the ground from the PCM when it's applied. So really one connection with your voltmeter into the Coil-On-Plug at the right spot. At the side the PCM supplies the ground, checks the fuse, checks the coil winding for continuity, and when you start the engine, checks the coil driver in the PCM. Three things checked, one spot to hook your meter. Hopefully, if you're not doing it that way, you will, because that can save some time. Now, for you techs out there that are using a scope, maybe you use it a lot, so there might be a little brush up. Maybe you learn one tip or two, or it'll just be a review. But if you're not using your scope very much, or you don't use it at all, you need to get on it, because you want to measure cars like this. This particular car has no problem right now. You want to measure good cars with your scope so that on those occasions, once a week, once a month, whatever, when you have the job that defies the flow charts, that defies moving coils and trying known good parts and all the things you do to try to save time in your diagnostics, you got to dig down deep. You'll be proficient. So brush off that old scope, whatever you've got it, build in a scan tool, get you a secondhand scope, whatever, and get scoping. What we've got is we've got 4 channels connected today on this Coil-On-Plug. So we've got the 2 wires I described, your power from the ignition and the ground supplied by the computer. We're going to back probe both of those. We'll see what the ignition does when we first turn the key on, and then we'll also see what the negative side does. Key on, engine stopped. It shouldn't do anything, no ground, so we should see power on both sides of that OCV, open circuit voltage, applied to that primary winding. And we'll also have, that's channel A and B. So channel A will be my power, that's my blue line. Channel B will be the ground supplied when the PCM wants the coil to fire. Channel C is going to be an amp clamp, which we already installed right here at the big breakaway connector. That's the purple wire to all these coils in the front bank here. And then channel C is going to be a little inductive probe. Very inexpensive, maybe $100 or so. This guy lays on top of the coil. Now, I actually tried it on some other coils and didn't have much luck getting a pattern on certain coils. It depends on how much insulation is preventing you from getting this little sensitive pickup to determine or give you a signal that looks like an old Sun or Allen machine, gives you that secondary ignition waveform. So you can see a lot into the eye of the engine with the secondary pattern. And the primary pattern is what we're hooked to also with channel B, the red circuit. That's going to also give us the same thing, because the primary is simply a scaled down image of the secondary. So let's go ahead and start the engine. Before we do that, let's do a key on engine stop. Watch the 2 lines, the red and the blue. Blue is supply voltage, channel A. Channel B, there we go, they both pop up. If you look at the exact measurements, the right versus the left, we've got about 13 volts, 12, 13 volts, so that's good. Now let's go ahead and crank it up and we'll watch the other patterns. Very good. So we're seeing a little bit of turbulence. I shouldn't say turbulence, I should say a little bit of noise. Dipping in the blue, that's my ignition feed. Open circuit voltage. Now we're closing it occasionally, but we're seeing the power feed to the coil primary. It doesn't change too much because it's the power feed. Takes some dips because when the coil is working, it's loading that 12 volt circuit down a bit, but it's mainly hanging in there at 12 volts. With the red, that's channel B. That's the switched ground by the PCM, and because it's switching a coil, an inductive winding, we're seeing all of the flyback voltage, all the inductive kick that you would normally see if you were using an old Sun or Allen machine. Got a 20-to-1 attenuator because it can be up to several hundred volts. A little tingle, won't hurt you. So let's go ahead and also put our inductive secondary wave pickup on top of number 1 coil here. And we'll do a little freezing. We get a good pattern. There we go. You can shut the engine off now. Now, in the brief period of what we had today, an hour on Coil-On-Plug, we're not going to get too deep into the scope. However, I just, again, want to encourage you. There are technicians that could, back in the day of the big box analyzers, when you had one distributor, which is very easy to hook a pattern clamp pickup around the coil wire, and then a signal pulse or a trigger lead off of some like number 1 plug wire, and see all the cylinders and all the events. This is going to be a little bit more work because you're going to be moving your back probing, moving your little secondary paddle pickup, if it works on that particular style of coil, around and watching things. But the beauty of it in a digital storage oscilloscope, DSO, is unlike what we used to have in the big box engine analyzers. You can store the pattern. You can actually save that, call that good Ford C.O.P. pattern. Then when you have a car come in that looks kind of funny, runs funny, you think it's ignition related, but you're not sure, you got to get deeper, throw a scope on it, get those good patterns you stored out, and compare them to what you've got on this vehicle. So the digital storage oscilloscope allows you to do that. So let's look at it from top to bottom. We stored this pattern. We look here, it's about between 12 and 16 volts. That's the blue line, channel A. That was just plugged into the power feed side of the ignition coil primary. This is a very simple 2-wire Ford Coil-On-Plug. By the way, 2016 moved to a 3-wire power, ground, and trigger. So you can't get this pattern of the primary ignition waveform on those vehicles. We see a little bit of a ripple of the 12 volts kind of dip down when the coil turns on. It's just kind of loading the 12 volts down just a hair. Channel 2 is in red, and we see over here the red scale. We are about battery voltage, and we come down to 0 and we jump back up. So channel 2 is actually what we're doing, applying the ground to what was 12, going through the winding of the primary. Now it gets pulled down to ground, so we see the 12, we see it go down to ground, and we see it pop up. It pops up to as high as, looks like 50 volts or better. So it was making a pretty good spike. That is the self-inductance of the primary winding in here. And this is the firing line from left to right. That's how long the plug actually fired. So we're seeing a scaled down version, voltage-wise, scaled down, almost exact pattern of what we see in the secondary winding, the part providing the spark to the plug. And then we see it then happen again. And by the way, the happening again twice in a row, that might perplex some techs. If you're a Ford guru, you know this. But if you're not, that might be a good question for you to type in later when we get into our question and answer series at the end of the broadcast. So channel C is our ignition secondary. So this is our secondary right here in tan. And so this is a mirror image. You see these look just like each other. Actually, that looks bigger, but if you look at the actual voltage scale over here, if we follow over here, it looks like we're having maybe, about 500 volts right now, and it spikes up to about 3,000 volts. So this was a few hundred volts, 50, 100, whatever. This is a few thousand volts. So we have different scaling here, but you can see the patterns are the same. We're looking for turbulence, a lot of turbulence. This is the modest amount of turbulence. If we see the pattern jump up significantly towards the end of the burn, that's representing that we're running out of fuel at the time. And if it stays fairly steady or has a little bit of a bell curve like that, fairly normal, again, you want to check as many cars as you can so you have a nice little pattern library going. And then finally on the bottom here, that it would be our amp clamp pickup. That's over here, channel C. Channel D was the channel D was the secondary pattern. Channel C in green is our current, so when current ramps up and it turns off. It ramps back up for the second event, and then it ramps back up. So they all follow each other. You can determine what a good pattern looks like, compare it to the car patterns you're currently having, and see if it's ignition related. Now, as I mentioned in the section on the hands-on looking at scope patterns, if you want to see all the plug wire, not plug wire, but all the coil-on-plug patterns, all 4, 6, 8, whatever you've got, so simply pop the fuse out for all the coils and pop a fuse buddy in where you can put the fuse in the side of the fuse buddy. So now all the current goes through this loop, and then with your scope and your inductive amp clamp, go around there like that, take a second channel of your scope and go to number 1, either the trigger wire if it's a smart coil, that's 3 or 4 wires, or if it's like the Ford 2-wire, go to the primary ground pulsed signal from the primary driver inside the PCM, and that will be a sync pattern. You know which one number 1 is, so with a firing order, you can simply look at all the patterns at once, span the time out on your scope, left to right is time, Up and down is always either volts or amps, and look at those signatures of those current ramp ups of those coil events. And when you find one that looks radically different than the others, that's the one that's intermittently breaking down, and that's the one you have to address with new parts or at least further diagnostics. Now, let's conclude on into our 4-wire smart coils for Toyota, Lexus, we'll see them on Mercedes, and a variation of 4-wire coils on General Motors. Now, again, there is a remote driver inside of here. So the signal we get to here is not high current as far as the pulsing trigger signal. It is a very low current signal to turn this off and on. We have its power and ground to power this thing up like any module, and that power is also there for the ignition coil secondary circuit as well. So, or I should say primary circuit as well. So all this is working off of 3. Now we have a 4th wire added. Unless it's General Motors, that 4th wire typically will be a feedback circuit. And it'll be in parallel with all the coils on the car. So the same circuit is hooked from coil to coil to coil in parallel. So when the coil actually fires, we get a signature on that wire. We get a square wave on that wire that tells that PCM, yep, this guy worked. It made some spark. So that's going to be what the PCM uses in addition to no current flow. It's open. Or, of course, the deceleration of the crankshaft for a misfire for any reason. Now, looking at this slide, looking at how all that works inside the coil driver, I should say the smart 4-wire coil module, we have power and ground like we would for any module, and then we add a signal wire like we would have with this 3-wire, GM or Honda, whatever. And the 4th wire we add, and that is going to be that feedback circuit. That's the diagnostic circuit, and that's going to go to a little chip, and when that coil does its job and it senses it actually made some spark, that's going to be the signature coming out from the right to left from that purple wire to the PCM. So it's a PCM input, and it's all hooked in parallel from coil to coil, as I mentioned. So nothing much we can do on the bench, but we can do a whale of things on the car, as we'll see coming up next when we look at some Toyota and Lexus on the car with our equipment. Now on General Motors products, that 4th wire is usually a reference low, a backup ground, a computer ground. So it's not a signal wire, a ignition feedback wire, it's just another ground. So if that's bad, it can actually on some models make its own ground through a power ground or a chassis ground, depending on the particular application in the particular Coil-On-Plug module. Now, looking at the scope issue, if you don't have a scope, get one. I'm going to encourage you. We get more into patterns here, but the bottom line is start going at it. It really is not going to get better when it comes to technology. You're going to need a digital storage oscilloscope no matter what you're working on. If you're working on intermittent mass airflows or data buses or direct ignition, or direct injection. It all boils down to good equipment. So we can actually do some power braking in the stall. We can go for road tests with extended leads going underneath the hood insulation into the car through an open window with another driver and their tech to do the driving, be your chauffeur, while you use your laptop or your Modus, wherever your scope is built into, and do testing on the road unless you have a dyne that you can bolt the car down and put a load on. Because as you know, some ignition problems only occur when you're under load and you're stressing out with a lot of kV demand with a lot of air jam-packed into that air gap, that spark plug. So let's take a look at pattern, basically the anatomy of a pattern. That very first upward and downward, the vertical line there, that's called the firing line. That's how many volts it takes to initially ionize or start burning across the air to make our heat source for air fuel to begin burning. The higher the compression ratio, the greater the throttle opening and load on the engine, and the less conductive hydrocarbons, gasoline in that mixture, in that little opening, the higher the voltage demand. So open secondary, high resistance plug terminals, the spring missing or corrosion inside the Coil-On-Plug boot, all those kind of things can cause that to be higher than normal. Lower than normal would be leakage, the boot leaking, water down in the head, in the cylinder, and surrounding the boot, or leakage from the frame of the Coil-On-Plug itself. All those things will make that lower than normal because electricity can jump to a ground a lot easier than it can jump sometimes across a gap. As we see the vertical line from that horizontal line this way, from the right Very far left, there's your vertical firing kV. The firing line of how much voltage from top to bottom here we need to maintain the air gap is a lot less than the initial amount of voltage to break through the air. But how that progresses, whether it does a lot of turbulence due to air and fuel issues, or whether it does a steady rise and then boom at the end gets much steeper, that would be from a mixture running out of fuel, a lean mixture. So all those things mean something. If we had more time, we'd get into it. At a later date, we may do a whole scope class, but just keep in mind that you want to look at known good patterns, record them, go onto IAT and other sources like that to find patterns and compare to what your customer's car has. When you get into a bind, you need to hook up heavy-duty equipment for diagnostics like scopes. We can see the current ramping compared to, let's say, a secondary waveform or primary waveform. They are essentially the same, except at a lower scale. Primary is several hundred volts. Secondary is several thousand volts. But you see the ramp up of the coil current-wise on the bottom picture, and you see it compared to what the secondary, the primary winding's doing. The oscillations is important as well. Some coils will only put out maybe an oscillation, maybe one oscillation. Other coils will put out 2 and 3. It's important to find out from known good information, known good cars, which models do what if you want to get deep into discovering whether you have a coil on its way out or not. So one last item on ion sense here. This is a really smart topic, really smart stuff when it comes to Saab and some other European cars. We have them on Harley Davidson and BMW motorcycles. We have them on Isuzu cars and trucks. Ion sense is where we have a normal spark plug and a fairly normal coil, but the electronics, if it's Coil-On-Plug and ion sense, way different. Still makes spark, it still makes thousands of volts to jump that air gap, but after the air gap is jumped, the combustion event now occurs. We're on that power stroke. We'll take some voltage that we saved up. We made it go into a capacitor, and then we started applying that capacitor's output to the tip of the plug after the combustion event. And the way that capacitance of voltage, 80 volts, 100 volts, whatever, the way that capacitance discharges based on the shock waves, what's in the cylinder after the event. If there were shock waves from, we'll say, oxide of nitrogen, from NOx, so you had a knock cylinder pinging, that's going to be detected by the signature of the decay of that voltage applied to the tip of that plug. So we don't jump the air gap with 80 or 100 volts, but we simply watch the decay of that voltage stored up in the capacitor, and that's what tells us whether we have knock or not without having to have a knock sensor. So those are some advanced ignition components, been around about 15 years, but we'll start to see them grow in popularity as software and minor coil-on-plug differences become cheaper than adding wiring harnesses with multiple knock sensors on vehicles. It's done right in the cylinder as opposed to a microphone on the side of the block. Let's go ahead and take a look now at some really smart coils and that feedback circuit on the Toyota Camry behind me, looking at what we can do with a meter and a scope and an amp clamp. Got a late model Toyota Camry here with a P0352. We got cylinder number 2 is down, the mill's on, and we've got a code for the Coil-On-Plug with an issue. Now, the first thing you always do, the manual tells you to do this in the flow chart, is to make sure you push to make sure it's snapped on, because they can come unlatched and look like they're snapped on and they're not. But that's not the case here. So I went ahead and set up for back probing the connector. Terminals A, B, C, and D, 4-terminal type coil, meaning that the drivers that control the solenoid, or the winding, I should say, for the primary side of the coil, those drivers are buried inside the little coil pack module. So the Coil-On-Plug module, it's got the transistor is going to turn the ignition primary circuit on and then turn it off, which is going to then induce the secondary voltage and make our high voltage to our spark plug. So we're not going to be able to really see any kind of a pattern if we had a scope to look into the primary like we would, let's say, with a 2-wire Coil-On-Plug, like some of the older Fords and Dodge and so forth that have been using for years. The Toyota, the 4 wires are power and ground because it is a module, so we got to make sure that's good as the first step. And then we have a trigger signal from the PCM every time we want cylinder number 2 to fire. We're going to turn on a transistor. It's going to be a 0.5 volt square wave kind of thing. And then we're also going to have some feedback if the coil actually kicked and did its job. Now, just like the parallel circuit for power to feed this coil is the same circuit as for all 4 coils, that feedback circuit is the same for all 4 coils. We'll just see a different kick for each individual coil when it's its turn to fire. And that's how the PCM makes sure that this thing is indeed producing a spark. It's making some action going on. So we're going to use these little AES wave back probes here and slide between the terminal insulation, or the rubber insulation I should say, that covers and seals out the terminal, and actually back probe it, butt it up against the metal terminal of the wire itself, which we have here. So red is our power from ignition, black is our ground. That's just so this Coil-On-Plug module can wake up and start working. And I'm just going to go ahead between the two on DC volts. And if I don't see a good 12, 13 volts with my Midtronics battery charger on here, a little battery tender to keep this thing up, I should see maybe at 13 and a half volts. If I don't see that, then I'm going to look for a voltage drop on either the power or the ground. I'll check them both. But if I've got good 13 volts with presumably a load of the little module, not a lot of load right now, that's going to be a first step here. So we'll back probe in here directly with our meter. So this is showing you guys that just use the meter, some things you can do. And we've got 13.3 volts. There's no need really at this point to go a little deeper. We could, if we wanted to, back the pins out or actually disconnect the connector, get some mating male pins and put a substitute load in there like a light bulb or something and do a voltage drop that way, but I don't think we really need to do that at this point yet. We've established good power and good ground. Now let's just see what we can see in regard to resistances of the actual module. Now this is going to be some things that aren't going to necessarily be in the manual, but just if you're curious to see what's going on, we'll turn it to ohms now. And we'll go between ground. If we can have the key turned off, because we don't want a live car here. All right. So here's our trigger input. Measuring between it and ground, we've got about 326 ohms. We have some kind of circuit there. It's not an open. Nothing really is going to tell us a lot here, because we're not going to be able to measure this coil like we would a normal coil, because it's a smart Coil-On-Plug 4-wire setup. But now this should show us how much resistance is in the entire circuit, and that's over limits. And there actually could be a diode in there. In fact, that's going to be the challenge that we'll run into with a lot of these Coil-On-Plugs, is that if we use the old-fashioned meter to measure, let's say, this older Ford 2-wire C.O.P., and we go between these two terminals, that's the primary winding. Just like a good old-fashioned coil that we've used for years, an old tower coil, one of these old GM coils, we can measure between the primary windings. We have, let's say, a half an ohm, whatever. We can also measure between the secondary output and the primary windings, because the other side of the secondary goes to the primary. And the side of the secondary that goes then to the spark plug goes spark plug. You can't do that with the more modern 4-wire coils. So what we can do, we can use a scope at this point and see what kind of trigger we're getting. Before we do that, let's just for grins see what we can get with a meter alone. So I'm going to go between ground and the trigger that the PCM provides to the coil when we are cranking or running the engine. So let's go ahead and start it up and see what we get on voltage, and we'll put it on frequency. All right, start the engine. And as the engine slowed down, you can see that frequency on my fluke meter. It's now at 6 hertz, 6 times a second. That's how many times number 2 cylinder is being given the command to turn the primary winding on and back off. And if we want to go ahead and look at frequency over here on the feedback circuit. Now remember, on Toyota, Lexus, some Nissan, that's a unique circuit that is connected in parallel to all cylinders on the engine, and we're going to see some kind of a square wave anytime any of these coils pops, makes spark. So we're seeing about 26 hertz there. So that's telling you you've got a signal. So that's telling you the wiring is good between the PCM and this coil. And we have a signal that the coil is putting out, or at least 3 of the 4, or 2 of the 4, whatever, but there is a coil putting that signal out, probably 4 of them. And we also seen on the blue connection, that was my trigger to make that particular number 2 coil power up, saturate, turn on, turn off, make spark. That's working too. Let's go ahead and shut it off. Now, if you have a lab scope built into your scan tool, standalone lab scope, like a nice 4-channel Pico PC-based scope, or maybe you just got one of those little single-channel scopes that you can pick up for a couple $100, get scoping. You're going to be using it for a lot more than things like this, but this is bread and butter, so you don't use this level of diagnostics every single day, but you need to be proficient at it enough to where you can use it once a week when you get the tough job. So what I'm going to do, I'm going to take an amp clamp. It's going to be in channel 3 of my 4-channel scope. There we are. And it's going to go around the ignition feed wire, which is this blue wire I probed with the red. So I just have an inductive amp clamp, but instead of hooking into the meter, it's going to be hooked into the scope. All right. Now we're going to take channel A. That's going to be my trigger from the PCM, what I was measuring a minute ago with the fluke meter in frequency mode on voltage, frequency. Trigger. And then channel B, that's going to be the feedback. So we can see the feedback of all coils working, doing their job, reporting into the PCM. And for number 2, our cylinder in question, we can see what's going on with the trigger from the PCM. So now let's go ahead and start it up and see what we have for current ramping of how the coil turns on, as well as those square waves from the input from the PCM to the coil, turning it off and on, and the output of the coils feeding back to the PCM. We can see 2 square waves here. The blue one's a little bit fuzzy. We're going to have to capture it here real quick here. Here we go. So we captured this in time. The red is indicating the signal from the PCM to the coil, telling the coil's module, transistors, turn on. The blue is the feedback of all the coils. So we would see more of these if we squeeze this pattern down with a little bit more time involved on the screen. We'd see all 4 coils doing the same thing, making this little pop. And the green is our current. You see the current ramps up, and it gets to a certain point, and it ramps up a little bit differently. That's a normal looking current waveform. We want to see it gradually turn on. If it just turned on very quickly, it's telling us we've got an issue with that coil. If it gradually kicks up like it does and comes up to a few amps, that's what you're looking for to see if you're getting a good coil and a good signal. So whatever was causing this problem with the code for the P0352, that problem is intermittent, and we'll have to go looking further, possibly get this coil warmed up and see if it breaks down under temperature. But for now, it's looking good. Well, there's the high end of things. Let's bring it back down before we close and give you guys some questions and let you ask me questions. Let's bring it back down to reality. Use all the senses that God gave you. I mean, the smell. You look at the connector there, it looks burnt, possibly some corrosion, rust, whatever. Also smell if it sees anything burnt with the coil. Observations with your eyes, looking for any kind of arcing, any kind of carbon tracking, not only on the coil itself, but around the coil, any insulation, the boot, and of course, the spark plug itself, the porcelain. And finally, look at your scanner. Anything you can see in your scan tool, including fuel trim. When you have an ignition misfire, that's going to be a lot of unburned air in that air gap that never got burnt. So as it went out the exhaust valve, it got in across that O2 sensor, and the O2 sensor saw a very lean mixture. It wasn't really lean, it was just a lot of unburned air from a cylinder misfire, ignition-related misfire. A lot of unburned fuel make the cat hot, but the O2 doesn't care about that, it only measures O2. So when the O2 is low voltage, lean, trim goes positive, but not as positive as a lean misfire. So let's say an injector's not working, that kind of a lean misfire can be 20, 25 positive % on fuel trim, whereas an ignition misfire might be half of that. Both will run the trims high, positive, but the fuel trim will be much higher when it's a true lean misfire as opposed to an ignition misfire. Also, looking at the hash on the O2 waveform, whether you're using a scope or you've got a really quick, fast scan tool and you can graph it very well. If you see a lot of hash, especially on cars that don't have fuel cut out when they have an ignition misfire being detected, let's say a P302, you don't necessarily turn the injector off in some older cars. Newer cars you do. So OBD-II has evolved over the years. On those cars that do shut the injector off, now we have basically the hash issue is not as bad. But when the injector is on and we've got air and fuel and the air being measured by the O2 sensor, we'll see a lot of hash, and that is commensurative of an ignition misfire. So those are things you can look at. Let's go ahead and take a look at some questions and let you guys ask questions for me. I appreciate you hanging out with me this last hour of your afternoon. It's going to be a question about an open circuit. We're going to start out with the primary winding of a coil, and then we'll apply the same question to a secondary. And here's how it goes. What happens when the primary coil winding goes open circuit? A, there's always a misfire. B, this is on Coil-On-Plug only, by the way. There is usually a DTC. C, both A and B, or D, neither A or B. Make your choices now.
All right, Dave, our numbers are in. We've got 25% saying B, 67% saying C, with 8% on D.
Thank you, Christian. Well, the C as in Charlie's have it, both A and B. If the primary winding is open, show's over, folks. No spark, period. If it's a single coil car, it doesn't start. If it's a Coil-On-Plug, you got one cylinder at the very least. It's got that open circuit that won't have spark. And you'll usually, of course, get a DTC. Depends on the algorithm for setting the code. Should occur pretty quickly. So answer is C, both A and B. Now let's reverse the scenario here. This next question, same way, but it's the secondary winding of the coil that's got an open circuit. So do we have A, always a misfire? B, usually a DTC, often a DTC. C, both A and B, or D, neither A or B. Make your answer now.
All right, Dave, our numbers once again are in. We've got 36% saying B and 64% saying C.
The 36th percentile have it. When you have an open circuit in the secondary, unless it's really a wide, huge gap of, let's say, a half an inch or something of coil missing, when you have an open secondary, it just typically just burns through it. It jumps across it. Remember, secondary has high voltage. It jumps gaps in the spark plug anyways. It can jump a gap at the rotor and distributor cap contact on the way to the spark plug. So a lot of air gaps can be basically taken care of with secondary ignition. They'll break down though. They'll arc and they'll misfire under load, but they may still fire. So there's always a misfire? I would say no. But is there often a DTC? Certainly. When it finally does misfire under load, you may set that DTC. So remember, secondary, I've seen coils that were totally open, old and new, on the secondary. Depends on how open it is. It may go ahead and just jump that open, bridge that gap with a spark, and go on out to the end until you really need all the spark you can get, and you don't have it, and that's when you get the occasional misfire. So B is the correct answer. Next question, two-wire, so we're back to, let's say, a Ford or a Dodge. Two-wire coil-on-plug secondary circuits can tie to the spark plug, and where else would it connect to? A, the coil driver trigger circuit. B, the power or ECM supplied ground to the C.O.P. C, the diagnostic feedback circuit. Or D, EST or HEI ref. Make your answer choice now.
All right, Dave, our numbers are in. We've got 7% on A, 73% on B, 13% on C, and 7% on D.
All right, well, this is the answer I put, and after looking at this question a little more closely while you guys were answering, I thought, you know what? A, actually, depending on how you interpret it, I could give you extra credit for that one as two. But the point I'm trying to make here is that with the two-wire coil-on-plug, as we've seen on the bench, you can go to either one of these primary terminals, the power feed, or the one that the PCM supplies the ground to, which is what I'm talking about in B, and you'll see the other end of that coil secondary circuit. Now, A is kind of close because if you thought of the coil driver trigger circuit as in the PCM, and that wire going forward to here, that would also work as well because it's the same circuit. But this truly doesn't have a trigger driver circuit built into it, so that really kind of in my mind when I wrote that question. Let's do one more here. The scope waveform of a primary pattern, a primary circuit of the ignition coil, that waveform is the exact but opposite mirror image of the secondary. True or false? Exact but opposite, like inverted. Is that true or false?
All right, our numbers are in once again. Ooh, we got 5% on true and 95% on false.
Very good. The false have it. It's not an actual mirror image. It is a scaled down image of the secondary. So very good on the false there. And last question, an intermittent problem with a COP can be caught by doing what? Diagnostic methods here. A, swapping COPs cylinder to cylinder. B, using an inductive secondary scope pickup. Or C, using an amp clamp and a scope on the power feed wire to the coil. Or D, all of the above. Select your answer now.
All right, Dave, our numbers are in. We've got 5% on A, 5% on B, and 90% on all the above.
All the above is definitely correct. Very good. I guess everybody was paying pretty close attention. I'm going to turn it over to the questions and I'll try to get best answers I can from the field. Let's see what we have out here from you guys after watching this.
All right, we've got a question here, and he would like to know, you mentioned 20 amps at the coil. This is the initial amperage and not sustained, correct?
Correct. In fact, if you had a fast enough scope, you could see some inrush of the sudden surge of a 0.6 ohm load applied to a, let's say, a 14.5 volt supply power from the battery being charged with the alternator charging. But it's not going to be sustained. It's just for a few milliseconds of on time. The dwell, we used to call it with the old point condenser days. And because there is one coil per every spark plug, they don't always have to have the coil off and on continuously for all 6 or 8, like the old distributed systems. So therefore, overall current measured over time is much lower. And that's why, because 2 reasons, these don't turn on as long, as often as these older coils, and they're not oil-filled tower coils to dissipate some heat. You would never want to power them up, power and ground on a bench, and let them cook and heat up like we did in the old days. That's a surefire way to see if you got a bad coil. Yep, you do now. So don't power them up with power and ground. Watch them while they crank or run an engine.
All right, man here says that if you can use the trigger, you can freeze the pattern rather than trying to capture with the space bar in regards to scope usage.
Yeah, that may be a pico feature I just simply don't do. I use my mouse and hit the little red stop button, or I use the space bar. But yeah, anybody's got good pico tips. I know IE10, I think, has an actual pico forum just for those users. And other scopes are the same way. I've used the OTC 2-channel, little job you can fit in your pocket, USB connection to your laptop. Pretty nice little scope. Really, any scope is a good scope if you start using it. And if it's pretty crude, simple, 2-channel, even the 1-channel little job looks like a cell phone you can stick in your pocket, that's a good place to start. But whatever you got, good at it. If you want to upgrade it, that's great. But yeah, it's a good comment on the storing patterns.
All right, we got a man here interested to know, how can you detect/measure internal tracking on a Ford COP?
That has always been an issue. In fact, some OEMs have had a specification of how long a coil, whether it be a DIS coil or a Coil-On-Plug, can withstand open secondary conditions before it starts tracking internally. The only way you can really bring the beast out, so to speak, of carbon tracking in a coil is to do either in the factory, load testing, or MacGyver it on the car, which means a dyne under a load, looking at a scope, or on the road with another driver while you're operating your scope and you're watching the same thing under load. You're looking for a breakdown. What you'll see is normal kV demand for your firing line and a normal, line left or right as how long it takes and so forth, how much spark burn time we have. That'll all decay. We'll have a very low firing line because it didn't take much to jump that gap as it did to go through the cylinder. So you're looking for a breakdown of spark under the loaded conditions. Otherwise, there's no looking at it because it's internal and there's no real testing. Although if you had a simple 2-wire Ford, what I might be tempted to do, and I've seen this in the Toyota manual for spark plugs, you would never do this test with a Coil-On-Plug Toyota 3 or 4-wire, GM 3 or 4-wire because of the electronics. But if you just got a plain old simple primary and a secondary winding, and some terminals and so forth, you could take a Fluke 1587 or similar mega ohm meter that puts out low current but up to 1,000 volts of energy. It's usually used for checking those orange cables on hybrids to see if they got a leak somewhere. You won't get shocked if you touch this 1,000 volts. You'll get tingled, but it won't hurt you. But I've seen it in the Toyota manual checking out spark plugs themselves, going between here and here with the Fluke 1587, because Toyota uses that tool for their hybrids, and they're putting it on a good old-fashioned secondary circuit to see if it leaks. Basically looking at the resistance value, should be 2 giga-ohms or whatever, unless it's leaking, then you'll see some number much lower than that. You could do that here on the secondary. It shouldn't hurt anything. That might be a way of flushing out that carbon tracing issue.
Wonderful, wonderful. We've got a question here. On Coil-On-Plug, is the primary usually isolated from the secondary circuit?
On the 3 and 4 wire Coil-On-Plugs, yes. On the 2-wire, like this Ford or a Dodge, no. Typically, you will see a connection between here and both of these wires. Within 0.6 of a difference between each other, you'll never notice it because 5,000.6 versus 5,000 ohms is indistinguishable when you get that high a level with your ohm meters. It'll just say 5K between either one of these terminals and here on most all, if I'm not mistaken, all the 2-wire coils.
Got another bit technical question here. They were watching your cutaway on the scope usage and amp clamps. Mike would like to know, is the output 4 times the signal? And he's also asking, do negative VE to signal hertz times 4 equals the feedback hertz? He's asking. So getting technical with our amp clamp readings now.
That may have got lost in the translation. I'll just say this. Mike, write this down. David.A.Hobbs, Hobbs, at Delphi.com. Email me directly. I don't care if any of you guys email me. You're all cool. Just email me and maybe we'll get a phone call or something going together to make sure we're on the same wavelength. I think I know where you're going, but I'm not sure. It's kind of a deep scope question about, time-based, volts-based, whatever. But we'll get it figured out. If you're really interested, give me an email, david.a.hobbs at delphi.com, and we'll hook up and we'll try and get the answer for you directly.
Excellent, excellent. All right, we've got a question from James. He would like to know, what was the blue trace when you had only the 3 on the scope?
Okay, that probably was, I'm going to guess, for the Toyota. Which application was that? Which test was it? The blue trace. The blue trace, well, that is, I believe that's channel 1 on Pico. And I was using, okay, if it was on the Ford Flex, the red vehicle, that was used for just B+, to see if I had a good power supply, see if I was getting a voltage drop, basically, to the power source, to the simple 2-wire Ford Coil-On-Plug. So the purple wire is what it was, the one I amp clamped, and I think that was a green trace, the amp. When I amp clamped, that same wire, I back probed it at the coil just to see what the voltage level was. Never mind the current ramping, just what the voltage level was. So that was the blue wire, or the blue trace. The red trace, channel 2 on the Pico, was the on-off ground applied by the coil driver circuit in the PCM. And that was giving me my secondary pattern, or primary pattern, I'm sorry. Good questions.
Excellent. Hey, thank you for your answers, Dave. That's all the questions we have tonight. I would like to thank all of you for attending this live stream event in Delphi's training series powered by AVI.